I unfortunately could not be here for the other talks, but I looked at the schedule, and it looks like a great and diverse set of talks on, how to scale machine learning, what kind of algorithms should we be implementing, what are the frameworks at all levels of the stack, how do we improve efficiency. And so today I'll try to give an overview of the different, is that okay? Yeah. An overview of how to design algorithms with a view of different applications in mind, how to design scalable methods, but at the same time, what are the trade-offs? Is it that typically systems performance and algorithm design don't always go hand in hand, right? It's easier to be modular and do them separately, but if you try to integrate them, there can be a lot of gains had, and I'll show you some examples of that. So, I'd like to think of artificial intelligence and machine learning, not just in terms of the algorithms we use, but really about the data and the infrastructure put together, right? That's why I call it the trinity, because it's the totality of all this coming together that creates successful applications. Many times we mostly think of just the algorithms when, especially in research, we are developing new algorithms, testing them on standard benchmarks. But in production systems and in the real world, there'll be usually new use cases, so no existing benchmarks, data may not even be available, you have to collect data, and then how to run that on different compute infrastructure, and what level of compute would we need. And so that's why we need to think of all this together, right? And this current deep learning revolution would not have been possible without the existence of large-scale labeled data, as well as large-scale compute from GPUs. And it's the flexibility of deep neural networks when you combine with the power and parallelism of GPUs and the availability of large-scale labeled data that gives us the success of deep learning today. And so given the excitement that this has generated, a natural question is, where do we go next? Right? What are the next generation algorithms? How do we design them? How do we implement them? How do we scale them up? And there are some ingredients I'd like to give today. So first of all, the main shortcoming of current algorithms is it's extremely data hungry for labeled data. Right? And in so many domains, we may not have enough data. I mean, even in computer vision, which is the poster child of deep learning, there is still not enough data in many applications. For instance, for face recognition, we've seen issues of fairness and bias when there are not enough examples from minorities, as an example. Right? So issues like that where in any application, there's always going to be need for more data. And the question is, can we replace it with something else? And that's where I'd like to think of incorporating different kind of inductive bias and structure into our algorithms. When we run convolutional neural network, convolution is an inductive bias. Right? It means we are incorporating translation invariance in our network design. The question is, can we now make that more sophisticated? What other kinds of domain knowledge, priors, and structures can we incorporate in the algorithms? And some examples that I'll show today are, some are structural, others are domain-specific. So in terms of structural inductive bias, you can think of, right, the structure in data itself being informing the neural networks, and convolution was one example of that. So I'll show you how tensors extend matrix computations to higher dimensions, and that can be also a strong form of inductive bias. Now, if you recall, neural network layers are currently all matrix computations. And in GPUs, we've parallelized them very efficiently. But what if we take everything to more dimensions? What if we design neural network layers where there are higher order computations? And how can we scale them up? How can we parallelize them? What are the benefits? So that's something I'll go deep into in this talk. And naturally, you can think of other kinds of structural priors like graphs. If you have relational data, then it's natural to use graphs as a form of prior, and graph neural networks have been very popular in the recent times. Similarly, you can think of other ways to use priors, although I won't go into details in this talk. On my website, you can see lots of examples where we can use other kinds of symbolic knowledge. If you're doing processing on math equations or partial differential equations, SAT solvers, there's so much of symbolic rules or axioms you can incorporate, right? Everything need not be learned from data. And so the more knowledge you can already embed, and then the rest learned from data, it's that intersection that would be powerful. So how do we have hybrid systems, hybrid neurosymbolic systems that can do both? Right, that can reason symbolically. At the same time, they can, give you numerical answers. So combine the power of classical symbolic reasoning with data-driven neural network approaches. So we have designed various frameworks to do this. Another important application is when we go to the physical world. If you want to launch robots, whether it is autonomous cars or drones or walking robots, they have to satisfy the laws of physics. And this need not be learned from scratch. Sure, in a game like AlphaGo, you can have an intellectual exercise of how well will it learn from data, right? But in the real world, we can't afford to just hope that it learns from data, and there'll never be enough data to learn that. So for robustness and for data efficiency, we can embed the laws of physics as much as possible and only learn the unknown parts. In one of the applications, we showed how you can improve drone landing by only estimating the unknown aerodynamic forces, which is hard to model. But there are so many other things you can already derive from your model and specifications of the drone. So those kind of applications can benefit a lot from reasoning about what's already known and how we can embed that into the model. And lastly, perhaps the emerging one that I think will be critical in the next decade is the role of simulations, right? There's never going to be enough real data, but theoretically there's infinite amount of data in simulations. But the challenge is we can never recreate the complexity of the real world or the variations in the real world. So there'll be a domain gap between the real and the synthetic data. The question is, how do we design algorithms that can do sim to real? Go from the simulation domain to the real domain and know to expect that there'll be domain shifts. How do we do that robustly? No, we don't want an autonomous car trained on simulations to go crash in the real world, right? So instead, we are using the synthetic data to improve the safety of those cars. So how do we get the best from simulations and account for domain shifts? I think we'll see a lot of this in the coming decade. So to go a bit deeper into what I mentioned about tensors. So indeed, if you're writing deep learning code, there is input tensor, right? Your data is expressed as a tensor because you have many dimensions in your data. If it's an image, it's typically 3 dimensions. Video is 4 dimensions, and so on. And as we collect rich multimodal and higher dimensional data, tensors will become even more important. So to begin with, we can think of tensor as a multidimensional array where you collect the data, right? But the thing is, how do we keep the structure of multiple dimensions as we propagate information through the neural network? So the neural network has many layers, and currently we only do matrix computations in these layers. So can we have better inductive bias by keeping tensor structures in the layers? So that's what we can do and think about the tensor layers. And indeed, if we want to think of tensors, they're extensions of matrices to more dimensions. As with all abstract math concepts, docs make it accessible, friendly, and fluffy. So that's your overview of what a tensor is. Right? So a point is zero-dimensional. Vector is a line with a length and direction. Matrix has rows and columns. Tensors now extend to more dimensions. A third-order tensor is a three-dimensional cube. This you can visualize. So people ask me, what happens when you go to 4 dimensions? I can't visualize. I tell them to go read a book called Flatland. This is a novel that was written in 1850s, and there it's an imaginary 2-dimensional world. All the living beings are in 2 dimensions, and there's a 3-dimensional monster that invades the world. It's a fascinating book in many different dimensions, literally. So I encourage you to go read that. And the idea is you don't have to visualize an object in order to process that, right? So most of the visualizations we try to do in 2-dimension and 3 dimensions to get intuitions, but really these mathematical concept is applicable to any dimension. And the main idea is when you're projecting your higher dimensional object to a lower dimensional one, you lose information, right? So this is easily seen, especially you see the cube there and it projects down on the wall. You cannot get all the information in the cube just in that 2D. And this is the intuition of why maybe matrix layers are not completely the right thing to do, are suboptimal for processing data tensors. And if you think about what a neural network is doing, it's taking an input like an image and coming up with an output like a category or a label, right? So that mapping is also a tensor itself. And so that kind of mapping could be better expressed when you also do higher order computations as your primitives. And so that brings us to the point of what's a new computational primitive? I told you that the foundation of GPUs is the BLAST primitive, right? BLAST stands for Basic Linear Algebra Subroutine, and at the heart of it are matrix-matrix computations. You do matrix-matrix products. Through that, you can express essentially the whole array of linear algebra techniques, and you can implement neural network layers. And now the question is, if I want to extend it to more dimensions, I can similarly extend the notion of matrix product to higher dimensions. And what you see there pictorially is now this 3-dimensional cube, you're multiplying along multiple directions. And we call it a contraction because you tend to contract and come up with a smaller object as the output. And so this now serves as a new computational primitive. And with this, we can build layers of neural network. And so that's the basic intuition that we can now extend this to many dimensions and come up with all kinds of ways to express tensor layers in our networks. And as an example, there is the standard neural network, right? There's a standard convolutional network. The first 2 layers you see is convolution operation. When you're doing convolution, it keeps the spatial information. Because you're processing your image, it kind of keeps through space, and that's how you get the activation map. On the other hand, when you come to fully connected layers, in the standard networks, you flatten those activation tensors, right? So meaning you just make it a one-dimensional object, you ignore all the spatial information. And then you go forward, you do ReLU and so on. But the thing is, what if we retained the 3-dimensional information throughout the network? That, to me, is the first step of extending this to tensor layers. And that's what we did. We can do the tensor contraction operation that I displayed in the previous slide. So now you're learning separate weight matrices along the different dimensions rather than one monolithic weight matrix in the fully connected layer. And in the last layer, it's something what we call tensor regression. Again, you can parameterize the weights to be low rank and compact. So the benefit of doing this is by incorporating inductive bias that the data is three-dimensional and there is spatial information, we can come up with far more compact networks. So we can save the number of parameters in these fully connected layers by a huge amount and still retain accuracy, as much as 65% in some of the networks. And so that's the benefit, that we don't have to always have these big, bad, massive networks, right? We can now but also make them compressed and robust and generalizable by using better inductive bias. And so you can think of this as a more global form of compression by using tensor computations. When you do pruning or quantization, they're much more local, right? They're only reasoning about one neuron at a time, whereas this is doing it all jointly. And so this is one instance of how you can use tensors. So there are several extensions from there we took. You can do tensor layers in different parts of the neural network. The extension that I'm excited about is for sequential models. If you want to do time series forecasting or other sequence predictions, it's hard when you have to predict way into the future. Right? The standard recurrent networks have deficiencies in that. They only have short-term memory, and that's why the latest language models no longer are recurrent or LSTMs. Right? And on the other hand, they're massive. They're essentially taking the whole sequence together and reasoning about that. So is there something intermediate in the sense there is still a sequential transition of the hidden states, but on the other hand, with tensors, we can express higher order correlations better. And that's what we did in this work called tensor train RNNs, where the idea is instead of one hidden state, the bottleneck propagating forward, we look at a window of hidden states and find low-rank tensors that express the higher order correlations between them. There are lots of details in the math, but the intuition is you're better propagating the higher order correlations in time. And so the hope is the information in the higher order correlation that matters for forecasting gets used better, and we get better forecasting results. And that's what we saw in this work, where the blue is the LSTM, the baseline LSTM, and the red is the tensor train LSTM. And you can see that the forecasting accuracy, or in this case, the forecasting error, it was much worse for LSTM, especially as you went way forward. I don't want to just predict what happens in the next time step. I want to predict 10 time steps and so on. This is challenging, and this is where tensors can help. And in fact, the tensor train LSTM was a smaller network. It had smaller number of parameters than the baseline. Right? So it's possible to get networks that are small and efficient and at the same time having better accuracy. And so it's possible to get best of both the worlds. And as an extension recently at NVIDIA, what we did was to ask, can we do the same with video prediction? Video prediction is perhaps one of the hardest tasks now. It's high dimensional, your input is high dimensional, your output is high dimensional. If you want to do this 10, 20, 30 frames down the line, this is extremely hard, right? And even the biggest models can't do a great job at it today. And so what we did was we essentially did convolutional version of the tensor train. The idea is convolution is essential for images and also for propagating forward in time. So we built convolution operations along with the tensor operations. And what we see is, compared to the state-of-the-art as well as the baseline, it's able to propagate long-range correlations much more effectively. Here you see even up to 38th frame, which is way ahead, right? It has to generate all the way up to 38th frame forward. The last one is the best one we have. And you can see that that's sharp and able to keep track of the correlations all the way through, but all the other models just fade away. They just don't know what to do that far into the future. And same with another data set where the actions need to be recognized, and you see like it's still sharp, way ahead, up to like 28 frames in this case, whereas the baseline model just loses track of it. And so the idea is you're able to retain long-range forecasting capabilities by using higher-order correlations, but these are also smaller models. These are smaller than the baseline. They're definitely smaller than the state-of-the-art models. So the idea is, let's just keep building big models, and we'll get to singularity. I know people have told me that is not possible. So we need to incorporate the right structure and inductive bias. And with this, that means we can also go bigger, right? But with the right inductive bias, we can solve more challenging problems. And that's the way I view the ecosystem today. So Tensorly is an open source software where we've incorporated a lot of these functionalities. The idea is it has multiple backends, including PyTorch and TensorFlow, and it's in Python. So you have these tensor layers already available. You can add your layers to it and train end-to-end. So as a simple example here, if this is in PyTorch, you can see that there is a tensor layer you can express. You can ask what kind of tensor representation you want, and just define it as a layer, and after that, it's all like the same as PyTorch. So this kind of integration hopefully makes it accessible and available to a larger community. So like I mentioned, so far I didn't talk about performance upgrades with tensors. The idea is because you're blocking into more dimensions, you have more abilities to parallelize and hence higher efficiency. So cuTensor is a library that I think got launched this week at Supercomputing. So the idea is there is now a new set of primitives that are accelerated in CUDA, and it's a matter of time where it'll be connected to frameworks like PyTorch and TensorFlow, and we can also get the power of GPUs to further accelerate these tensor operations. And yeah, so you can see here the three facets again came together, right? Tensors are efficient to represent rich data structures we obtain today, whether it's multidimensional or multimodal. And then tensor algorithms can keep this dimensionality information through the layers of processing in a deep neural network. And then on the compute infrastructure as well, we can accelerate tensors. So the trinity, again, comes together very well with tensors. So since I have just a few minutes left, I wanted to give other examples of where there is free lunch. You can get compression, but at the same time, don't lose accuracy. And in this case, this was for multi-node training. If you want to use multiple GPUs and train our model, there are two frameworks, right? Either you can do parameter server or you can do ring. And we implemented both of them. But the idea is if when communication cost becomes the bottleneck, you want to be able to compress them. And so we asked a simple question. What if the machines just sent the sign of the gradient? I mean, GPU or machines, right? Whatever is a single node of computation. So when they only send the sign, what happens? They don't send the full gradient. So now this is one-bit quantization. And it emerges that the performance is almost the same in terms of accuracy. So the accuracy is nearly the same. You get no drop in accuracy, but of course you get savings in communication, and so better throughput. So the numbers I won't go into, but the main idea is you can get a free lunch with gradient compression. And in fact, depending on the model, some of the language models, you can even get more gains by compressing the gradients. There's also some nice theory showing that why this is possible. I will not go into that, but it actually shows that you don't have to do anything, just compress the gradients, and it will work in most reasonable circumstances. And we are also now trying this out on the MLPerf benchmark, which, if you keep track of it, there was an announcement just last week on how NVIDIA beat on the inference benchmarks. This time it was the inference, the previous ones were training, and it's emerging as the de facto benchmarks for performance in machine learning. And so there are lots of things we can add on top of the current best performing systems in terms of better algorithm design, better inductive bias, and better also theoretical analysis, saying what are the right things to do. Another framework that I'd like to introduce is the Rapids, launched by NVIDIA, which is open source. And the idea is, instead of just optimizing a single machine learning algorithm, can we optimize end-to-end pipelines? Especially ETL is a bottleneck in so many real applications, right? So if we can remove the passage between CPU and GPU and keep it on the GPU and accelerate it, there are tremendous gains that can be had. If you go to the website, you can look at XGBoost and so many frameworks that are accelerated now on GPUs. So I encourage you to check that out. Other frameworks like NVIDIA ISAC is where there are robot simulators, high quality, physically valid photorealistic renderers and simulators. And so with this, we can do so much in simulation before going on to the real world. And this is just an example of that. Yeah, and same with autonomous driving. We are experimenting our algorithms now on these photorealistic and physically valid drive simulators. And there's so much of testing and safety critical analysis we can do there before taking it to the real world. Yeah, so that's the main principle that, what I wanted to emphasize was data, algorithms, and compute infrastructure coming together. And as we go to the next generation, I believe we'll have more use of tensors and higher order structures to express our data, and then have algorithms that would not only use neural networks, but also frameworks like sim to real, how to go from simulation to the real world or between domains, how to incorporate structure, priors, and other domain knowledge. And also in the computing front, not just faster computing, but also more computing on the edge and more energy efficiency and so on. So there's lots to come in the next decade. Thank you.